Thank you. Thank you all for coming. So let me start by addressing perhaps the most contradictory part of my title, which is continuous combinatorics, right? Because combinatorics is the study of discrete structures. So what do I mean when I say continuous combinatorics? Well, it's very simple. We are still interested in studying discrete structures, but they're going to be very large. And the idea is that we're going to be able, because they are large, we are going to be able to use tools that are typically associated to continuous structures to study them. More specifically, what do I mean by a large structure? What I mean is that we're going to say, well, there's some sequence of structures, and we're going to define some notion of convergence and try to say, well, there is a notion of convergence, so we're going to construct a limit that is actually continuous in a certain sense. And then I can use tools like topology, measure theory, and things like that to study these kinds of structures. Now, this started sort of with the theory of graph limits. So you might have heard these names, but now it covers a much more general kind of objects. It covers more general combinatorial objects. More specifically, I mean, formally, it covers anything that's a model of a fixed first-order universal theory in a finite relational language. But if you don't know what this means, just think of a hereditary class of objects. What this means is that I give you some class of objects, and every time I give you an object in this class, it has some sort of vertices. If I look at some subset of vertices, the object induced by that is still in my class. So for example, graphs have this property, hypergraphs have this property, linear orders, colorings, triangle-free graphs, permutations, a bunch of things you can define like this. A non-example would be something like a group, because you cannot really induce a subgroup in any set of points of the group, right? So these are just to have some examples in mind. And the idea is that because we have these hereditary classes of graphs, this allows me a very nice definition of counting in this, because anytime I look at set of vertices, I can count and I can check what is the thing that's induced by that. So I can define this thing, which is just the normalized number of embeddings of one object in the other, right? And this has nice properties exactly because of the hereditary class.
What does normalized mean?
Just normalized, but number of embeddings is just functions from M to N, vertices of M to N, do the normal, the usual normalization, just so it's between 0 and 1. Once I have this, I can define this very simple notion of convergence, which is to say, I give you some sequence of combinatorial objects in one of these classes, and I'm going to say it's convergent if, well, the sizes are going to infinity, so this is capturing large, and every time I give you a fixed object of my class, I can compute the densities of this object, and I'm going to require all of them to be convergent sequences of numbers, right? So it's very natural because we don't really know what convergence of objects is, but we know what convergence of numbers is. So might as well compute these numbers and require all of them to converge. They can converge in any rate. I don't care if it's uniform or not. Just all of them need to converge. Okay. So what's the kind of thing that you can do with this? Well, you can actually encode this into a limit object. So this is kind of like the classical theorem for graphs. Lovász and Szegedi showed that if I give you a convergent sequence, the limit can be encoded by something called a graph. So it's some object. I'm not going to really get into details. If you don't know, don't worry. It's just something that actually encodes the limit. You can compute densities of finite graphs in this guy. And the reason why it is encoding limits is because these numbers that I know, these convergent sequences of parameters that I know that converge in my sequence, they're actually converging to what I can compute in the limit. And conversely, this is a correct characterization because every graphon is actually the limit of some sequence. Now, there's some annoyance between, you can have more than one graphon representing the same limit, but this doesn't really matter for what I have to say today. Now, as I said, this is sort of like the starting point. It was done for graphs, but now we know way more general results. People have started studying more other kinds of combinatorial structures in an ad hoc manner, like directed graphs, hypergraphs, permutations. And we also know more general kinds of limits that deal with these universal theories, these arbitrary hereditary classes. So we have like limits like five algebras, L limits, and theons. Now, I should say, you might think that it's strange, right? Once you cover universal theories, why do you need more than one limit? These limits look very different, and some of them have some advantages and disadvantages against the other. So it is actually useful to know these various different limits when you're trying to do applications. Now, this is sort of the more abstract part of my talk, but I will kind of focus a little bit more on application. So the first kind of application that you can get out of these kinds of things is that Well, they are limits of finite structure. So you're getting these limit objects, they do say something about asymptotic behavior of finite structures. So for example, people have used these theories to prove things like regularity lemmas. So this like L limits is very much related to this regularity lemmas. Flag algebras was a very powerful tool to obtain some new extreme of combinatorics results, and peons have been used to study some quasi-randomness results. But today I'm going to talk about a kind of a different kind of application, which is not really about the objects, but rather about the theory. And this is, there's some sort of relation to, it's sort of inspired by model theory. So one way that you could look at model theory is to say, well, in model theory, you're trying to study a theory by looking at variation of its infinite models, right? So for example, if you know some of these terms, if you don't know, just don't worry. People studying model theory, one of the things they were interested in is something called Kiesler's order that somehow encodes complexity of these complete theories. And this led to discovery of structural properties like stability and IP, SOP. So we heard a little bit about this name stability on the previous talk. And this is kind of very curious because these are really structural properties that are important because you can find applications that are completely outside of the infinite world. You can find applications to the finite. So people now have these stable regularity lemmas, which we heard a little bit about in the previous talk. We have NIP regularity lemmas. And there's also even applications to some fields of TCS. So for example, we know now that, well, okay, this was not really due to model theory, but back learning is characterized by NIP, it's bounded DC dimension NIP, and online learning is actually characterized by the stability property. So it's very natural to ask, continuous combinatorics is sort of doing the same thing, it's constructing not an infinite model, but the limit of finite models. So can we use this? Can we look at variation in the limits of a universal theory to study the universal theory? So I'll give some examples of something that goes along these lines. So the first kind of example, it's Erdogshinal conjecture. So just a brief reminder of what it is. It's based on Renzi's theorem. So here's Renzi's theorem, if you forgot, which I don't think you have, but it says that every graph on n vertices has an inducive graph of size log n, about log n, that's a clique or anti-clique, right? So it's Erdős because Erdős gave this boundary. Now, Erdogshinal conjecture is about improving this bound. Of course, you cannot really improve. There's a construction. It's the random graph that kind of attains this. But what I mean by improve is like this. You say that a hereditary class of graphs has Erdogshinal property. If instead of finding something logarithmic, you find something n to the c or some constant. Of course, the constant depends on the hereditary class, but it's much larger, like it's polynomial, quote unquote, size instead of logarithmic. And the conjecture just says, well, okay, we know that this is not going to hold for the class of all graphs, but as long as you have a proper hereditary class, there should be this constant. That's what they asked. Is it true that you have this constant for any proper hereditary class? It's a very hard conjecture. We know some cases of classes that have this property, and some are sort of trivial, but some are very, very hard. I mean, there's a single paper just to prove a single class. I should just point out, you know, here's that notion of stability appears again. So can we do something using continuous combinatorics to this Erdogshinal conjecture? Well, not quite. We can do something about a variation of this. There's a variation of this that is actually very amenable to continuous combinatorics, which is what we call approximate Erdogshinal property, which says, well, instead of trying to find something polynomial sized, I'm going to try to find something linear sized. But I'm going to require that I'm looking at a convergence sequence of graphs, and I'm going to also say almost homogeneous. So it doesn't need to be a clique or anti-clique, you can miss some edges. And it turns out that this, okay, so this is sort of the finite formulation of this, but this is very useful to think in terms of continuous combinatorics because in graphon language, you're asking for every graphon to contain an almost homogeneous subgraphon. It's exactly equivalent. And if you like something along the lines of arithmetic combinatorics, you might appreciate the third one, which is if I give you a countably infinite graph in this corresponds to trying to find a positive upper density almost clique or anti-clique. These are all equivalent. And this I'm going to do everything for graphs, but I should say most of what I'm going to say has actually generalizations to finite relational languages. So this is something that you can study with graphons. And it turns out that stability notion that I said before is very much related to this AHP. So just to tell you what is stability, stability is about these half graphs. So half graphs are graphs that look like this. So you have a bunch of x's, a bunch of y's, and the x's are connected to the right with respect to y's. And the class is called stable if you have an upper bound on things like this that you can see. It's basically like that. And what you can prove is that a graphon has this almost clique or almost anti-clique if and only if it has an almost stable subgraphon. So almost stable means there's an upper bound in which you almost don't see these half graphs of larger than this upper bound. And of course, you have the corresponding equivalences with convergence sequences and this countable infinite graph. You can also do the same kind of thing. As I said, there is a generalization of this to finite relational languages. So stability also sort of controls this approximate Erdogshinal property. Now, another thing that is curious about this is that the Erdogshinal property is a very hard conjecture, but it turns out that you can completely characterize the approximate Erdogshinal property based off of which graphs are in the theory very easily. So this is the kind of theorem you can show. You can show that I give you some hereditary class, and you can find these large almost cliques or anti-cliques if and only if this class does not completely contain a certain class C, which is just the family of induced subgraphs of recursive lobes of C4. Now, this is kind of very nice because it completely characterizes this approximate Erdogshinal conjecture, and in particular, it implies that this is a much stronger property than the usual Erdogshinal property, which is not entirely clear because here the cliques are larger, but you're allowed to miss some edges. So it's actually a much stronger property. Now, I'm not going to get into the proof of this, but I think it's I should say there's a generalization for K-hypergraphs and finite relational language is sort of in progress, but it's much more complicated than this, so I'm not even going to say how it looks like. But let me say a little bit about what happens on the negative side of this, because it serves as a good entry point for my next topic. What happens on the case where you do contain this class C is that in particular you contain all these recursive lobes.
What is a recursive lobe?
You just take C4 and then you take each of the vertices and you replace it with the C4, and then you take each of the vertices, replace it with C4, and etc. And then you do this finitely many times, but everything that is a subgraph of any finite steps is there. Or you can also say, do it countably many times. This gives you an uncountable graph, and any finite subgraph of this is in that class the same. Okay, any more questions? Okay, so once you contain all these recursive lobes of C4, what you can check is that this limit is actually the problem. It does not have a large and almost clique or anti-clique. And there's a different kind of perspective on this, that it's the perspective of persistence that tells you that why is this going on here? So for this perspective, I need just two definitions, which is like this. If I give you a graph on W, Q of W is just the graphs that have positive density in it, and P of W, it's like this persistence class, is the guys that have positive density in every subgraphon of W. And if you think about these things like this, saying that a certain theory or a certain family of graphs has AHP is the same as saying that no graphon of P has both the edge and the non-edge in this persistence class. This is what is going on. That's the only way you're going to avoid a large clique or anti-clique. Is if every subset actually has lots and lots of edges and lots of non-edges. And it turns out that this guy is a problem because the persistence class is exactly the class C. Is exactly that class C that appears there. And if you think about it in a different way, so for example, let's say that a family is persistent if it's P of W for some graph on W, it turns out that this class C is the smallest class that contains the smallest persistence family that actually contains the edge and the non-edge. So this comes from sort of a different kind of study, which is the study of persistence. And it turns out you can characterize this persistence in terms of the substitution operation. So what we can show is something like this. I want to check when does a family is actually persistent. When is a P of W for some graph on W? And it turns out that this is exactly when it's closed under the substitution operation and induce a graph. So substitution is what you expect. You take the graph, you take another graph and substitute it here, you just plug it in here, it becomes the edges. Right, so the recursive loop of C4 is just substitution of C4 inside itself a bunch of times. So you can characterize persistence like this. In fact, you can even characterize strong persistence. You can find graph such that both P of W and Q of W is equal to your family. And because of this, so there is a generalization. And because of this, this is why this guy is actually the minimum obstacle for AHP, because C is exactly the closure of the edge and the non-edge under substitutions. So that's what was going on there. Now, the last thing that I want to say is sort of related to what I said so far. So as I said, so this AHP is a very strong property. So you might be wondering, okay, what is, and it implies EHP, right? The normal Erdogshinal property. So what would be a weaker property that maybe has some chance of still implying EHP? So let's try to think about things that are weaker than cliques or anti-cliques. So for example, we saw these guys that have P of W equal to Q of W. Let's call these graphons weakly random. So it's called weakly random because the weakening of a quasi-randomness property, which I'm not going to get too much into details. And as I said, so cliques and anti-cliques are like this, quasi-random graphons are like this, but this WC4 is also like this. So you could ask, what about the property where I'm trying to avoid having a weakly random subgraphon instead of just having a clique or anti-clique? And it turns out you can also characterize this in terms of what are called prime graphs. So these are the guys that are not substitution of smaller graphs, and you can characterize, well, sort of characterize under the assumption of closure under substitution. You can characterize families that have this WR property as the ones that have infinite anti-chains of prime graphs. So hopefully these kinds of results tell you that you can use these continuous combinatorics to reveal some structural, some important structural properties from hereditary families of graphs and theories like that. Oh, I think I had just there's also a generalization of this, but I'm not going to get into details. So that's sort of what I had to say for today, and this is a list of other things that I work on. If you're interested in anything of this list, just you can talk to me later. Yeah.
Are there any questions?
Are you interested in non-approximate versions of Erdogshinal conjecture?
Oh, yes, yeah. So are you interested in trying to understand how this, well, so as I said, this does imply the Erdogshinal property, but we have been trying to, understand how much does this reveal about the usual Erdogshinal property. It turns out that, unfortunately, I don't think it reveals too much. In particular, I don't know if this even gives you a new class that satisfies Erdogshinal property, but it does start revealing a little bit of structure of these patterns in this substitution. Like, for example, this whole WR thing, discovering that it had something to do with infinite anti-chains of prime graphs. I think it was somewhat of an achievement, because it didn't feel like this would have anything to do with these weakly random things. So it's more of like trying to explore how these operations that behave well with the usual Erdogshinal conjecture, what other things they also characterize. It's more towards that.
All right, let's thank Leonardo again.